Why don't I can I just key it in here? I gave him the number, but can I?
Hello, hello.
Oh, there he is. Hi there.
Hello, hello. How you doing?
Can you hear us okay?
I can, yes. Can you hear me?
Yep, I can.
Excellent.
Are you getting picture of us?
I am, yes. You're all looking very well.
We'll turn it around in a second so you can see the class.
Okay, doke.
So,
should we set up the sharing?
I'm going to introduce you to the person who will be introducing you, Charles Graham. It's good to,
okay.
I was going to say good to see you, but I don't see you.
Well, you know, the downside of video is I'd have to be dressed.
And who wants
of course I am.
So Charles, thank you very much. That's great. So come on around here, Charles. He can see us. We're just going to hear him. So get to know each other a bit.
Hi, Dr. Richardson. How are you?
Fine, thanks. Kurt will do. How are you doing?
Oh, not too bad. Where are you located right now?
I'm in Phoenix, Arizona.
Oh, okay, fantastic. How's the weather?
Some splendid blue skies.
Ah, nice. I'm going to start things off with a talk today with a little bit of a story, and then I'm going to move into a formal introduction. And I hope that I got everything correct in your formal introduction. And please correct me as I go if I have an inconsistency.
Well, as you'll hear from some of the things I'll say, nothing is true about anything, so I'm not too fussy.
Yeah, sounds good. That takes the pressure off me then.
Whatever you say will be wrong, and it'll be even wronger in 6 months' time. So, no problem. I'm just trying to make sure I've got my screen set up my end, so make sure I'm sharing the right pages. So,
so you guys just switch to.
I'm just going to share the right screen. Let's try that one. Let me move this out of the way. What are you seeing? Are you seeing
yeah, I can see
a PowerPoint type thing?
That's correct, yep.
Excellent. Okay, well, that bit's good. And if let's see, I want to. So these things are showing up when I drag a different screen on. That's showing up your end.
Do you want the projector on now?
Sure, we can do that. And actually, I'm going to start with a bit of a story. Maybe we can move the camera towards the center of the classroom just for that part.
To show him.
Yeah, just to see. That way he's not looking at a blank wall.
Okay. So Charles is about to introduce Kurt.
Oh, there we go. Or we can just leave there else.
Oh, okay.
That works.
Yeah, that works.
Hello, everyone.
Okay, guys, we're going to start. I decided, though, today I'd start things a little bit differently. What I do is I would tell a story about my adventure yesterday. Because my adventure led me to a little bit of discovery about something, and I did want to share it with you. So I was in Walmart yesterday, and I'm shopping for food. And I'm shopping for food because, as we all know, after a few weeks of eating in the Habitat cafeteria, it gets a little dry, it gets a little boring. So I'm in Walmart, I'm buying some fruits and vegetables. My mother would be happy because I'm buying fruits and vegetables. And I'm nearing the end of my adventure, and I think to myself, you know, I should buy something for the class, some snacks that we can hand out and pass around. And I think that's a great idea. I pat myself on the back, and then I start thinking, what am I going to buy? And I'm thinking, I'm processing, and it takes me a while to think. And I come up with an idea. It's nearly October 31st. Halloween's around the corner. I'm in Walmart. They've got to have Halloween candy. So I'm in the back of the store at this point, and I know the Halloween candy is in the front of the store. So I take a few steps forward, and then I think to myself, what am I going to buy? And I have the answer. Those little chocolate bars. I love chocolate. So that's my answer. And it brings me back to a little boy when I'm trick-or-treating in Calgary. You know, I'm walking the streets October 31st, soliciting myself door to door asking for candy. And it's a weird tradition, right? I don't think they have that tradition in the UK. But I'm thinking about that, and I'm thinking about how I used to judge each house on the candy they gave out. Now, if I got my little chocolate bars from a house, I gave that house an A. Now, if they handed me some sour candies or an apple, perhaps, I gave them an F. And matter of fact, if they gave me like a really affluent house and they can afford it, they gave me the big full-size chocolate bar, I gave them an A plus. I remembered where they lived and I said, I'm going to go there first next year. And then at this point, I'm about halfway to the front of the store in Walmart, and I think, what if there's somebody in the class that doesn't want the chocolate? What if somebody, when they went door to door and said trick or treat and asked for candy, they gave the house an A to the house that gave them, for instance, the sour candies. The candy did not give them that. Maybe the chocolate bar was the F. So this posed a problem. So this was a complicated problem. I didn't know what to do. I got to the front of Walmart. And of course, it's Walmart. There is aisles of Halloween candy, walls of Halloween candy. There's boxes of chocolate bars, there's boxes of candy, and I don't know what to do. So I think to myself, what happens if I buy one box of the chocolate bars and one box of this other candy, like these sour candies? And I'm like, no, I can't afford that. That's too much, you know, so I get rid of that idea. And then out of the corner of my eye, I see this box of Halloween candy. It's on its side, but the box, it's this one. It looks like this. And I think to myself, Cadbury, you have got this. Now, I said the box was on the side when I first saw it, so it actually looked like this. And I saw something in that box. What I saw was a Connectin diagram of sweets. In the bottom left-hand corner, I've got one of my favorite chocolate bars. I've got the caramel chocolate bar. Pure, elegant, awfully sweet. I love it. Things are simple for here. I'm happy. I'm simple. Okay? As I move up, I go to the Wonder Bar. Not as sweet. Things become a little more complicated. And as I move around the diagram, I leave the chocolate regime altogether. And I go towards these Maynard gummy bear things, okay? Not very happy. Matter of fact, as I go down, I get to my sour candies. Now I am not happy. I want to get back to where things are simple, where things are sweet. I want to get back to my caramel chocolate bar. Matter of fact, I will trade you all the sour candies I have for one of your caramel chocolate bars. So Cadbury, they will not be polarized between the chocolate lovers and the candy lovers. They have a solution in the middle. And this reminded me of Dr. Kurt Richardson's quasi-critical pluralism. The position somewhere in the middle between that of the idealist and that of the realist. Now, you know me probably as somewhat of a realist in the class, and that's true, but I'm not suggesting realists love chocolate and idealists love sour candy. But you get the picture. So I'm sitting in Walmart, or standing at this point in this aisle, faced with all this candy, holding this box, and this epiphany of God. I'm thinking about complex systems theory. I'm thinking about Connectin diagrams. I'm hoping I'm going to get an A in this class. I think I should name this box. So in honor of the talk today, I decided to name this box candy. The box of quasi-critical sweetness. So I encourage you, please, to grab a piece of quasi-critical sweetness and pass it around. So that's my story. So now to the more formal part of the introduction. Here we go. Dr. Kurt Richardson is an active researcher in the field of complexity-based thinking. He has a particular interest in the nature of boundaries and the relationship between form and function in complex dynamical networks, and how they might provide insight into the management of complexity in all walks of life. His paper, The Hegemony of the Physical Sciences, An Exploration in Complexities Thinking, is a required reading in this course, MEM 661,
And it shows us that no single type of discourse should unquestionably dominate our understanding of complex systems. Dr. Richardson has an honors Bachelor's of Science degree in pure physics from the University of Nottingham, a master's degree in astronautics and space engineering from the University of Cranfield, and a doctorate of philosophy and physics from the University of Southampton. He has worked as an engineer, physicist, and publicist. In his work, he has developed various multi-methodological approaches to complex systems, which mix both the physical and social science perspectives. When he is not conducting research, publishing, editing, or solving complex engineering problems, he likes to work on his golf swing, play music, and practice Taekwondo. Ladies and gentlemen, it gives me great pleasure to introduce you to Dr. Kurt Richardson.
Wow, well, thank you for that. That's I just think of myself as somebody like sitting in front of a computer screwing around, but that makes it sound all very highfalutin and important. So you can see my screen, okay? I believe. You can see the graphics? Yes? Okay, so what I wanted to talk about today was the topic of what is real. And this can seem rather abstract and who really cares, but really this is at the heart of everything we do. It's the heart of how we generate knowledge of things, how when we think we have some knowledge of something, what we can do with that knowledge. And there is a tendency to of a sort of naive realist perspective where what we see is what there is. When we have knowledge of things, it's somehow absolute, or we don't spend too much time worrying about what the shortcomings are. So there's a lot of philosophy. There's a lot of philosophy books out there that you can read. What's interesting with in the last 20 or 30 years is complex systems theory. Kind of offers a way to explore some of these deep questions from a fairly realist perspective. I mean, it's almost a physical argument for pluralism, which or physics-based argument for pluralism, which is somewhat surprising. So what I want to talk about is, what does the complex systems bring to bear on this particular question? So, I'm pressing the wrong button there. Let's get onto that screen. Okay. So what is it about complexity that creates so many problems for us when it comes to learning about things and implementing what we think we've learned? Well, all too often, we kind of regard causality in a fairly linear way, or at least we assume we can approximate it in a fairly linear way. So, we have some object affecting another object, car crashes into tree falls on house. And we assume that tree, car, and house are, reasonable objects of analysis, and we proceed from there. Yeah, as said in the next bullet there. So there's a lot of theoretical physics, a lot of maths, a lot of just everyday thinking, where we try and reduce the problems to this. Physics, there's a lot of nonlinear mathematics there, but to solve it, often we try and reduce it to something much easier to understand, something that can be solved analytically. So we kind of cherry pick the easiest solutions. And it's even some of the theories at the heart of physics, like Einstein's field theories. We still hear about solutions to that being presented, years and years after it was first presented, because it's a very rich formula. There's no one solution, and there's many ways to approach it. So, we spend a lot of time just finding ways to cut through the complexity, to simplify the linearities to it, so we can come up with something tangible that we can say, and hopefully it gives us some ability to predict behaviors and take meaningful action. On the complexity side, it's a very different model. I mean, it's I don't know how much you've talked about systems, but at a very high level, we're talking about lots of nodes interacting, non-linearly. So causality isn't this simple X affects Y affects Z. It's the result of many feedback loops, affecting each other, cancelling each other out, supporting certain behaviors and cancelling out others. It's it's a real mess. And also the objects that we use, the focus of the analysis, aren't necessarily obviously selected. I mean, when you start looking at the the environment, for example, or even, or I guess a good one these days with all the friction in the world between different groups of people is, what are the different groups of people? You know, once you draw a boundary around this group and say, you know, these are these sorts of people, is that a good object for analysis? How reasonable is that? You know, to how far can you take the assumptions that you had to impose to draw that group around, that draw that boundary around that group of people, to then start saying some things about them and doing some analysis? So these things aren't trivial, and all too often we just look at the world out there and go, "Ah, there, tree. That's easy. I can distinguish that from everything else. I'll work with that." And you know, in the world of, you know, mathematics, with the distinction between linearity and non-linearity, there are very few solutions to some incredibly simple nonlinear problems. You know, all the thousands of books out there are on, you know, linear mathematics and physics, all dealing with problems that are highly well, you know, they've been distorted to such an extent to allow a certain type of analysis to proceed. So, you know, you can write down the equations of a nonlinear system or nonlinear activity, or, you know, a theory about these things, but then solving them to try and make some predictions and understand how you might interact with that particular system or context just can't be done. So we see more and more on the harder side experiments in computation. So there's a lot of simulation going on, and if you look at climate change models, you know, they don't predict, you know, detailed specifics. They predict certain ranges if certain things continue in a certain way. There's lots and lots of caveats that comes with any of the conclusions that these kinds of experiments and simulations do. And then, you know, another area is soft systems methodologies, which you know, which are kind of an extension of the hard systems methodologies, and in some respects a response to the shortcomings of those approaches that were seen in the 70s and earlier. But part of the reason why the paper that I propose you guys read was written was because in America especially, I see management scientists, for example, regularly just dismissing soft systems methodologies as not real science. So, you know, why bother? Let's build a nice big simulation and spend $1 billion on simulating everything, and then we can come up with policies and the world will run just fine. So another aspect of this kind of line of argument is saying, look, there are more than one ways to solve this problem, and more than one way to explore it. Modeling's one way of doing it. Soft systems methodologies produce a different type of modelling and exploration. So I just want to give an example that just shows what a mess complexity introduces. Just think of a simple model of gravitation. So, you know, I'm not going to get deep into any physics here, but, you know, the force between two objects is given by this formula. It's analytically trivial. There's, you know, I think there's one feedback loop. So for this example, maybe we look at, you know, the interaction between the Earth, the Moon, and then the effect back onto the Earth. And, you know, Newton solved this. He proved that, you know, planetary orbits were elliptical, and, you know, it's very clever stuff. It's you know, he invented calculus through all of this. But analytically, it's trivial. It can be solved 100%, and you can start making predictions on it, assuming, you know, you can isolate this model. And so, as I say there, the two-body problem is not very interesting at all. So we jump to let's go to the next level. Well, you know, we're just going to introduce one more body to this system. Surely that can't do too much. So now we have three, you know, celestial objects out there, all interacting with each other. So now, instead of, you know, the one feedback loop, we now have four all of a sudden. Just by adding that one extra body, we have each one of those bodies interacting with the other one, and we have, you know, this big feedback loop going around all of them. So, but it still doesn't seem, you know, especially complicated until we try to solve it. And we suddenly find there is no analytical solution to this problem. You know, we can't do a page of clever maths and go, there we go, we can now predict the positions of all these you know, moons and planets in the future. But we can make some simplifications that will force the context into a certain direction, and we get stable solutions. for instance, just the solar system. I mean, given our short lives, and it looks like it's a fairly stable system. The planets just keep going around the sun, but in fact, that's just one possible solution to a very complex system, and the solar system's chaotic. And at some point, this stability that's there now won't be there. It's not an eternal clock that's just going to keep winding forward as we look at it today. And just a simple example of that is this is one of the solutions to the three-body problem. And I hope these animations show up your end and don't stutter too much. So we've gone from these simple elliptical orbits to something that's a real mess. And of course, this is one of an infinite number of solutions to this particular problem. So, we had a bit of feedback, we had an extra body to the problem, and all of a sudden now it's not solvable. I can set some initial conditions that will make these go around each other in a nice circular fashion, and look more like what we see in our solar system. But there are astronomers have observed systems just like this, behaving like this, with these complex chaotic orbits out in the real universe. This isn't just a theoretical thing. So we don't need much to get chaos is kind of the key there. One extra body, some nonlinearity, all of a sudden things get a bit tricky. So, what happens when we start looking at networks? I mean, we're trying to look at problems these days that have way more than three bodies in them. We're trying to understand, global politics and, very complex interregional conflicts. We're trying to understand, the role of social media and its impact on society. I mean, these aren't just three bodies going around each other. So we have problems with 4 feedback loops. So here's a very simple network. It's got 25 nodes in there. There are 75 connections. The top and the bottom plots are the same network. They're just presented in a slightly different way. So again, it's a bit more complicated than the 3-body problem. That had 4 feedback loops. We can't solve it. This has 2,345 feedback loops. I mean, we haven't got a chance in hell of solving this. Mathematics just doesn't exist. Some would say the mathematics will never exist to solve this particular problem. And for this one, I wrote a paper about this particular network. There's some rules added. There's a bit more detail to solve it, but this particular one has 20 different behavioral solutions, 20 different ways in which the different nodes can interact. And none of those can be determined in advance. You basically have to build it, run it, and count them. There isn't a shortcut to doing that. So that's a real limitation to what we can do. So, I mean, this paints a pretty dire picture. We need 4 feedback loops, and all of a sudden we've lost the ability to make fairly simple predictions. We look at any real-world situation. The number of feedback loops, the nonlinearity there would suggest there's nothing sensible we could ever say about it. But clearly, that's not the case. We have science, for example. It's done a lot of amazing things. F equals ma works very well in sublight situations. We've done an awful lot, given that supposedly none of this stuff should be understandable, given the complexity there. So why is that? This is one reason of why that could be. So this is another very, very simple network. And I don't know if you can see my cursor your end. Doesn't matter too much. But this is an incredibly simple system where it's just a row of squares. They can have a state of 0 or 1, or black or white, or dead or alive, whatever you want. 0 doesn't mean nothing. 1 doesn't mean something. They're just 2 arbitrary states that each one of the squares can be in. And we start at the first line here is how we decide how we kick the system off. So we've just randomly turned some of the squares to black and left some of them as white. And on the next row, that is calculated by this very simple lookup table. So we read this as here is a square that is currently as 1. If both of its neighbors either side are 1, then on the next time step, we're going to set it to 0. And another one over here, we have it's currently it's set at 1. Both of its neighbors are set to 0. So next time out, we're going to set it to 1. So this is all that this is it. There's no more to this system. If this was a model of the universe, this would be the theory of everything that physicists are trying to grab. There's nothing there, and yet we get this incredibly complicated pattern as we step forward. Again, it's similar to the 3-body problem. There's a particular solution here which is rather messy, doesn't yield to simple analysis, and the only way for me to predict what's going on this bottom row here is to run this thing forward, I don't know, 100 time steps and do the math. Every single step has to be calculated. There's no shortcut, no easy way for me to see where this system's going without running it. No analysis I can do, no clever maths. No rules of thumb, nothing. I have to run it. So that kind of, I think, well, okay, that doesn't help me very much. If this is a, albeit very simple model of what could be the real world, it kind of leaves me stuck. And then you start sort of noticing that there are some regular patterns in here. There's these kind of triangles moving forward. There's these kind of diagonal patterns, but big areas of this space are filled with a certain pattern. So let's remove that. Let's apply a filter to this that removes that pattern. A little bit of logic that will just go through whenever it finds that, remove it. And when we do that, we get this. A very different view now. Now it's it's much easier to see what's going on, what dynamics are going on here. And we could look a bit deeper and go, well, maybe this diagonal over here is a we can consider that to be a particle that's moving to the right, and here's another version of it moving to the left. And there seems to be some patterns here, and when the one going to the right and the one going to the left collide, there seems to be some reproducible interaction here. So let's go through this and see if we can uncover some rules. And if we do that, we can actually write down some sensible interactions about this, about what's going on here. So this is pretty amazing if you think about it. If we get the previous screen where we showed all the detail, imagine my first row had a billion squares on it. I have to go through each of those billion squares, do the calculation, move it forward step at a time. A lot of computation. It's all very simple, but a lot of computation needs to be done. Now I've moved to a level where, well, I don't need to bother with all of that stuff. I've got some formulas now, so all I really need to know is what particles are where they start, and I can propagate this forward. It's very quickly, very easily. I could even do it by hand if I was somewhat patient. This is looking pretty good. So that complexity I saw at the first one seems to be somehow we can rein it in and come up with some theories about it, some rules about those objects that emerged that seem to work rather well. But what's interesting about this is that I can't go back to that previous picture. This isn't reversible. I've applied a filter. I've seemed to have uncovered these objects in there. I've developed some rules that seem fairly efficacious. They enable me to predict. But it's also thrown some stuff away because I can't. My little algorithm I use to do that filtering, when it's put in reverse, doesn't get me back to where I started. So even though this description is very good, it's not complete. So that's one part of this. The other part of this is thinking about, well, what's really going on here? I mean, we just got a row of squares, and we're crunching that simple lookup table, and now we have particles. Are these particles real, or are they just something that we found by applying a rather favorable filter? You certainly can't get to these sets of rules by starting with the original physics, if you like. You can't start with there, crunch some algorithms, apply some theories to get these interaction formulas. You just can't do that. So what is the relationship between those two? The first thing we know, this makes life a lot easier. I can do a lot of calculations, make a lot of predictions. That's useful. I don't have to go back to superstrings to predict planetary motion. But it's also incomplete. It's not true. It's not correct in any absolute sense. These are very useful rules of thumb and give me some predictive ability. So maybe we could think of this as a chemistry. So at the one level we have physics, and of course chemistry is just physics. Surely, I mean, it's just physics manifesting at another level, which is a very flippant remark. But the thing to bear in mind is no one's deriving chemistry from physics. It may all be physics at the end of the day. The human body is all biochemistry at the end of the day, but who's deriving thought from biochemistry? I mean, it's we're fortunate enough that some filtering has allowed us to see this different kind of slice of reality that enables us to give us these rules. So we've kind of shifted. We've shifted ontology. We've moved from reality to some idealization of it, and that's given us some real significant power in prediction and understanding. So yes, we have thousands of feedback loops, but these things can manifest and interact in such a way that we have entities that if we apply the right filter, we can then see, and then we can generate some rules about them, try and understand how they interact, develop some theory. But at the back of our minds, we've always got to remember that in any absolute sense, we've taken a step away from what truth, if you like, with a capital T, to something that's somewhat more than a convenience. It's more powerful than that, but it's not absolutely true. It's a very useful tool. So why am I kind of harping on about this? When I first saw the results on that previous page, and I'm kind of still getting over it to some extent, because it really does make you think about, well, what is the relationship between the noughts and ones we saw on the grids, and the alpha, beta, gamma particles that we found when we applied this filter and wrote down our rules of thumb. So when we talk about anything, any of our knowledge, what is the relationship between that and what actually is? It's not a one-to-one mapping. It's not arbitrary. It's not socially constructed in isolation. There's complex interaction there between what we think we know, what there is, what will happen, what we think will happen. We can't just sit back and assume we come up with this clever formula and now everything will work the way that would suggest. And again, what is the relationship between the physical hierarchy of reality? From atoms to molecules to humans to societies. Each one of those, there seem to be some obvious objects there by which we can develop some rules about, but they're intimately determined by a layer below, and we have no way to connect those two. There's some tricks and tools in complexity, like the bottom-up computer simulation and stuff, but it doesn't really tell us how it happens. It just shows us that it does. So that first little example, it's called a cellular automata, and it's incredibly simple. And you might think, well, this is all well and good. It's a nice little tool. It enables you to play some mind games. But has it got anything to say about the real world? Well, a couple of things about it. The first thing is, if there really is a theory of everything, it's probably something that looks a lot like that. It's the most efficient way to generate such rich complexity. There really is no other way that we know at the moment that can create those kinds of emergent properties, those emergent objects that then have seemingly have their own types of behavior. And this is another example which might be a little bit more compelling, maybe. This is something called the game of life that a mathematician called Conway came up with in the early 70s. And it's a little bit more complicated. Now we have a big grid, and imagine this grid could be arbitrarily big in either direction. And we have three very simple rules. We have death. Well, firstly, each cell in the grid has a neighborhood. It has 8 squares around it. and those are numbered 0 to 8. It's, I don't want to get too much into the details, but you know, there's a rule that says if a cell has 0, 1, 4, 5, 6, 7, or 8 occupied neighbors, then we kill it off. Part of the logic is if there aren't many, then it dies of loneliness, and if there's too many, then you know, it dies because of overcrowding. So these are rather kind of superficial attempts to make it look like real life, but at the end of the day, we just want to have some simple rules that give us some simple behavior. So if an occupied cell has 2 or 3 neighbors, it gets to live to the next generation. And if an unoccupied cell has 3 occupied neighbors, it becomes occupied. So we have these kind of death, survival, birth rules. And it's been shown that this universe that this results in is not fundamentally any less rich than our own, which is quite incredible. I mean, where does this come from? These are 3 incredibly simple rules. The system itself is absolutely trivial. And yet it's it's impossible to solve. So let me just show you the extent of some of the richness of this behavior. And I'm hoping this animation will work. We don't need the music behind it. So this is going to show you some of the objects that lived in this universe, and they're found just by throwing in, you know, certain patterns and seeing what happens to them. So those 2 objects, you know, these objects moving diagonally down here, they're not in those initial rules. These emerge, and we can approach them as if they're, you know, self-contained entities. We can develop rules of thumb. We can develop theory. We can, if the grid was big enough, the patterns we see here, we can then jump to pull different levels of abstraction and observe more and more complicated objects. They've even found objects in this universe that self-reproduce. So these objects are, you know, are really very sophisticated. You know, here we see some being created from the interactions of these things called gliders. So again, when you're looking at this, you know, try and link back to where it's coming from. These 3 simple rules are generating a reality that is as rich as the reality we observe. And the rules aren't as simple as just, oh yes, this thing moves to the left, this thing moves to the right, this thing interacts with this one, and creates another one. There is no reason to not believe that if the grid is big enough and it's seeded in the right way, and you stand back far enough, i.e., you know, abstracted far enough away from that original grid, that you won't discover objects that behave as if they were making decisions. You know, they're not just doing the same thing over and over again. They have the appearance of autonomy, making independent decisions. And all of this comes from this ridiculously trivial example of a system. So although it's, you know, I'm not going to say that, you know, this is the basis of all reality that we live in. It is interesting to explore, given that this has, you know, is fundamentally as rich as our own universe. If it is like this, if these objects do represent or we are capable of, it is reasonable to say that atoms, molecules, and stuff are like the objects that emerge in this type of system. What can we say about them? Can we explore what does that mean for our understanding? Again, some of the questions I mentioned earlier. So, you know, the famous philosopher Daniel Dennett just said, you know, if you want to do philosophy or think about knowledge, you've got to get a copy of the software that runs this and just sit there, watch it, get drunk, watch it, get stoned, watch it. It's just staggering the amount of complexity that is in this universe. And to try and think again, you know, think deeply about the relationship between the rules that I might give to some of these objects and where they're coming from, given that none of them are explicitly in the rules that we, you know, that run the grid. This is emergent phenomena in action. So the next few bullets are really just some practical advice from this, and I'm hoping not too many of them are that big a surprise. I think there's philosophers for a long time have offered some insights into the relationship between knowledge and reality or ontology, and some rules of thumb on how you operate in a world of uncertainty and where your assumptions about things are not absolute, and things will change. And especially with the discovery of things like chaos theory, where small changes can lead to radical change further downstream. How do we operate in that kind of world? What I find interesting is two things. Firstly, that you can take a very simplistic physics-based model and argue for some of these points. The other side of it is I don't see much evidence that this goes on today at all. There's a few. You go to a complex systems conference or a systems theory conference, and they're lucky to be 200 people there. Turn up to a management conference and there's 10,000, and most of what's said is you just think, my God, where's this coming from? I mean, it's what you see is what there is, and here are some rules, and if you apply this, your business will thrive. You look at some of the campaign for Brexit, for example. Absolute garbage. Just the displays of an inability to critically think are just very disconcerting. If you look at educational programs, where's the critical thinking element in the curriculum? I mean, I did physics till I was 26, and was never given there was never a course on philosophy of physics. It was just assumed that you kind of as time went by, you drew some conclusions, like where they start off teaching you an electron is a point, and by the end of the course an electron is a cloud of probabilities, or light can be a wave or a particle, and it's just taken for granted that these are both good and that light can behave that way, rather than we don't know what light is, but these two different theories give us some insight into light. So I just don't see an awful lot of evidence that the bullets, which I will get to, is actually being demonstrated in much of society today. And I think education can play a big part of that. And for me, part of the reason for the paper was I was seeing, even with, there's a certain degree of arrogance within the hard scientists, within the hard sciences, the dismissal of like soft systems thinking that just drove me crazy, which is part of why I wanted to provide an argument for those kind of domains from a very hard physics perspective. So let's just run through some of these. So hopefully this is obvious. I should say I hope all of them are obvious if to somebody who spent a bit of time thinking about things and has read more than a few books in their lives and made a bit of an effort. All perspectives should be regarded as limited, provisional, and subject to change. Surely that goes without saying. Don't be too quick to hang your hat on one particular approach. This is stuff that if you sat there and watched Fox News for 5 minutes, you would immediately realise that these people don't see this at all, or at least they don't want to present things in this way. Critical exploration of ideas is essential. You may come up with a solution that works well in the short term, but if you're not prepared to accept that it's going to be increasingly over time, it's going to become the wrong approach. You end up stuck with trying to push something that's really lost its validity, and all the waste and problems that are associated with that kind of dogmatism. So do not assume what has worked before will work again. But at the same time, these things aren't black and white. This is not saying that what has worked before won't work again. It's it's not rejecting the possibility that reuse is possible. It's just don't take it for granted. What is working now will undoubtedly have to be altered if to continue working in the future. I mean, this kind of links to sustainability. I think some of the stuff I read on sustainability kind of makes me laugh, because they try and push a way of doing things and say that's sustainable. Well, surely sustainability, the first step of sustainability thinking is to recognize that nothing's sustainable, and the only thing that's sustainable is something that will change and adjust with time. Be on the lookout for evidence that your current approach is failing. This kind of made me chuckle somewhat when I put it down, because there seems to be rampant evidence that the more evidence to the contrary, the more people dig their heels in. They're not interested. If it doesn't match their view of the world, then it's clearly wrong, or I don't care. This is the way it is. Think about the circumstances under which your assumptions are valid. Assumptions there's a domain of validity for them. There's a jurisdiction where making them works, and informed action can be taken. But again, just don't take it for granted. So, and one here, all statements of truth come with caveats. No statement is true with a capital T, except this one, of course. So this is a, it might seem that this is somewhat a paradox. You can't make such a blanket statement as no statement is true. But like all paradoxes, I think they're fairly easy to get out of with a caveat or two, or just a slight reframing. So, except this one is my attempt to deal with the paradox of that statement. And just resist intellectual laziness. And you guys making a big effort not to be intellectually lazy. So this doesn't apply so much. But this is something I think more and more people realise is it's a lifelong activity. You don't go to school, get your degree, get a bit of paper, get you in a door somewhere, now just crank the handle for your career and make some money. This is a lifelong endeavour. If you're interested, I think it's somewhat emancipating to some extent, because getting caught up in your own thinking can cause all kinds of problems. So being willing to walk away from it and try something else, I think, is fairly key to your ongoing mental health. So I'm nearly done. I know I've gone on too long. If you've ever been to any academic conferences, academics are absolutely dreadful at time management. They get given 15 minutes and go in with an hour's worth of slides. So I'll try and wrap up fairly quickly and just throw these quotes up, and I'm sure we can share the slides afterwards if anybody's interested. So the first one here is from a philosopher, Feyerabend, and what he's really saying here is, just to kind of cut to the chase, is what we do is, we look out there, we're trying to make sense of something. There's some kind of filter that might be provided by a theory, some paradigm, some approach, some methodology, and that enables us to focus in on certain things, and we throw the rest away. We assume it's not relevant, and then we assume that the things we're focused on are the things that are real and important. Sometimes there are, sometimes they're not, but it's that interesting distinction that we make. We just assume that this is the right thing to be focused on. This is real. The rest of it's just noise. Well, that noise over time will show itself, and what you thought was real proves to be rather temporary, and it gets replaced. The other quote here is from a Buddhism one. There's what got me into Buddhism initially was, and I'm not a Buddhist, I just like some of the philosophies, was a paper on the de-reification of boundaries, and in there they talked about how boundaries are not real, but boundaries are essential for our ability to act, to make sense of things. So it's kind of trying to keep that tension alive, that we make assumptions to get stuff done, but remember, those assumptions are wrong. Sometimes you'll get away with them for years. Sometimes, they'll fall apart very quickly. And this is kind of referencing back to what I said earlier. We kind of trivialize the relationship between physics, chemistry, biology, sociology, all these ologies, both in the soft and hard sciences. The relationship is somewhat trivialized. In the case of chemistry and physics, we assume chemistry is just physics operating at a different level. I don't think enough people appreciate, or even enough scientists appreciate, that there is no way to go from physics to chemistry. I mean, the only way to do chemistry is to make some assumptions about the level of reality we're interested in. So this tells us that we're not going to reduce everything to physics. We have an argument to legitimate other perspectives, as long as they prove productive, enable us to act in some coherent way, with some useful insights, it doesn't matter so much whether they're talking about real objects. They're real enough. If superstring theory proves to be, the basis of a theory of everything, the only thing that really exists are superstrings. Everything else is an emergent manifestation of that. But that doesn't matter so much. As long as they're real enough that we can develop some rules, and also bear in mind that they're sufficiently real for the purposes of our analysis method, approach, whatever. And this one's always been one of my favorite quotes, partly because, or nearly entirely because, it comes from a physicist. And one of the most celebrated physicists of the 20th century. So there's this kind of popular view that which I think has some merit, to be honest, that physicists think they know it all. At the end of the day, everything's physics, and at some point we're going to reduce everything to physics, and it gives us detailed understanding and prediction. The top quote, the one from from Hofstadter, tells us that it might all be physics, but we're never going to explain it all in terms of physics. This one is telling us that if we, even with physics, what seems to be the hardest, most accurate, quantitative, rigorous science out there, even there, if we get too caught up with viewing it as a precise description of the real world, it's going to let us down. It's a very, very useful tool. It's very, very successful, but it's not right in any complete sense. In an absolute sense. And then I've always got to throw something in from Freddie Mercury. So, is this the real life, or is this just fantasy? It is to some extent just a fantasy. It's a constructed reality we're living in. But as it kind of illustrates with the previous modeling, it's not a detached fantasy. It's not completely arbitrary or made up. There is a relationship, a deep, complicated, changing, evolving relationship between what's in our minds and what's out there. I think I'm just about done, and there's one more little video I wanted to show, and we'll call it a day. And it's from The Matrix, and it's the part in The Matrix where Neo realizes he's the one. And I've always loved this animation, because it's a very useful visual way of showing that everything is. It does come back to it. Let me jump ahead. Or let's just focus on that one page. It was at 44. I lost my mouse. So I think this, I've always liked this animation in The Matrix, where it's just showing that everything is connected to everything else. There's a flow of information and energy between everything. And, even something we take completely for granted, as in 3 humans, or in this case, automatons in The Matrix, but, are not disconnected from everything else. No man is an island, who, probably heard many times. This takes it to an extreme level of everything really is connected to everything else. But the extent to which that interaction is relevant on any given context is something you have to discover. It's just not straightforward. It's a mess. You've got to think hard about things. There's no simple solutions. I mean, I'm kind of sounding a bit like a broken record now, but it's hard. It's important to really embrace that and understand it at a deep level, because I've been involved with management consultancy, and I've presented models to managers, like simulations, and they've gone, "Oh, great! If we tweak these dials, look what we can do. We can build a future for our company based upon this model, just by employing 20 less people, employing 500 more people, selling into this market." They immediately want to use the model as if it's some kind of mechanistic predictive device. Rather than a tool for exploring possibilities and for developing, portfolios of strategy and this sort of thing. So, it's one thing to understand this; it's another thing to kind of walk the talk, if you like. And although I hope a lot of what I said towards the back end seems almost obvious, I think it's fairly important for us to try and make as many people as possible aware and understand that this is the nature of the world we find ourselves in, and simplistic, trivial sound bites don't cut it. And it has impacts all over the place. I mean, the school curriculums aren't really aren't built around these ideas. You look at a lot of management science, it's not. A lot of the softer sciences, or in the management sciences, social sciences aren't. It's a bit of a hodgepodge. And I think I'll stop there as I've gone on 20 minutes longer than I should have done, Alice. I'm sorry.
Thank you so much, Dr. Richardson. I'm just going to make a comment. You said something that struck a chord with me. I actually went through a Bachelor of Science astrophysics program. And in that 4 years at university level, not once did I have one course or professor talk about complexity thinking, talk about a qualitative approach. And I was really surprised by that because, as a young student, especially studying physics, you learn about all these bright physicists, Einstein, Max Planck, Schrödinger, and they all exhibited, in my opinion, this train of thought, this philosophical, a philosophy kind of thought that really has allowed them to critically think. And they came up with, obviously, famous physicists, some great theories, and brought physics to where it is today. I mean, Einstein's a great example of that, taking physics from where it was at that point and coming up with something called general relativity. And to make that leap for me was always absolutely outstanding. I didn't know how he did that. So I think that's interesting that you pointed it out, and the fact that, in the hard sciences, we really haven't adopted that kind of form of thinking that well. And I hope in the future that possibly that kind of gets brought up into the school system, and particularly universities and hard sciences more so.
I think partly it's responsible for some the dearth of philosophy going on in schools. I mean, science. Good scientists don't see it this way, but there's certain caricatures of science that seem to suggest, well, why do you need philosophy? We know what there is. There's atoms and protons. I mean, that's all there is. And how do we develop understanding of those? We apply something called the scientific method, and you're done. So there's no need for any more research and thinking about epistemology. Ontology's done. Who cares? Why explore it any further? And I think that's a big mistake. But then there's areas of science that aren't like that. I mean, even in something as well established as superconductivity, the theory of superconductivity is based upon quasi-particles. They're not real particles. There is a model that recognizes a certain feature and treats it as a particle and manages to give us some explanation. The whole wave particle duality of light really hints at a deep philosophical issues in physics, and they're often just papered over, ignored, as if well, they just work, so let's not worry too much.
Now, I know your time is valuable. We do have some questions prepared. Do you have much time to?
I'm happy to hang around as long as you need. So I know okay. you guys have got a schedule. So.
Okay, fantastic. So we have some questions. We've actually prepared some questions as groups. We like to go through the groups and pose a question. After that, we'll open it up for some general discussion as well. So I could ask the representative T5 to come up. And please introduce yourself first and last name. And if you could also introduce what program the Master's Science Master studies.
Okay, that's good. Thank you very much, Dr. Richardson. That was super interesting for me. My name is Jonathan Reimer. I'm in the MSc program here in Environment Management as a program. I'm a giant philosophy nerd. Like, I feel bad for anybody who talks to me, so I won't digress into this too much, but I saw some really cool parallels. This is just a quick aside into William James and that whole pragmatic theory of truth school, and then as well Karl Popper's fallibilism and theories of scientific progress and such. On a more practical note, what we would like to know, or we'd love to get some input in, is a lot of us work in the hard sciences, or harder sciences at least. And on a practical side, how can we communicate our work and in ways that are still effective, but don't marginalize or trivialize people who are working in software sciences or the arts or complexity theory or whatever other non-science inquiries are out there. That's it.
Well, I mean, many things, and I haven't got the answers to everything by any means. But one thing one behaviour I saw that was particularly concerning when I did my PhD was I was told not to present negative results, not to present shortcomings of my proposals or my hypotheses, and that just seemed crazy to me. That scientific papers are written to, or presentations are given that dwell completely on what's good about it. And don't treat the shortcomings as much as as comprehensively as they should. If just that simple act, I think would help an awful lot, because then it's not being presented as some profound absolute truth of everything. It's being presented as a very powerful tool for thought, if you like, with some serious shortcomings and some limited jurisdiction. So on the physics side, I saw that a lot, and couldn't see that being a good way to proceed. And again, it's to some extent it's a result of the publishing environment academics find themselves in these days. It's coming from the top. Some of the guidance and churning out papers is a kind of a metric for success. Quality measures are much harder to grasp. So I hope that's one possible strategy. It's hard. I think in other areas, I mean, I think it's even more obvious. I mean, statistically, physicists are kind of spoilt when it comes to the statistical validity of some of the theories, because they score like R squareds of 0.99. In some of the softer sciences, people are using an R squared of 0.25 and saying, "Look, I've got a theory." I mean, it's there more than anything. It's a useful rule of thumb, and the limitations and the context in which you might find it useful need to be very clearly explicated. Otherwise, people just jump on them and start using them as if they were, deeply true. I don't know if that helps.
I would just say practically be more explicit about kind of the bounds, the assumptions you're using, the scope that you're actually treating this at. And,
well, think about it as the Facebook problem. How many people present themselves on Facebook as they're having this amazing life where nothing goes wrong? I mean, it seems to be something that's not just a problem within academic publishing and writing. It's everybody wants to put their best foot forward, and I'm not sure that's healthy.
Excellent.
Hi, Kurt. My name is Asa Pomunya. I'm taking a master's in science as well. We're wondering that we are experiencing complex systems and the favor it gives to the idealist approach of thinking. Can you provide an example in which abstract thinking has provided insights to a solution that hard sciences or traditional sciences could not or would not?
Sorry, could you say that again?
Can you provide an example in which traditional or hard sciences couldn't provide a solution to a problem and abstract thinking did? Did you get that?
Well, there's in just modern geopolitics, there's many examples of where pretending that the problem can be viewed as a physical problem, causes problems. We don't have to look too hard, do we? There, I think that's a. If you look at when I was doing work for the government in the UK, we looked at this. We looked at the Sudan. And they were quick to draw boundaries around different groups of people and say, these people behave like this. Then we build a model, and that's used to inform policies. And of course, it's a gross oversimplification, but it was required to enable some analysis to occur. And I think that happens all too often, where a problem. This isn't in the physics domain, but this is applying physics to some physics type thinking to a problem, with the belief that kind of approach should work everywhere because it's worked so well with atoms. So in that. We can't do that. Sorry, we can do that, but the shortcomings of that approach need to be fully understood. These methods just aren't easily transferable from one domain to another. In physics specifically, I mean, if you look at Newton, great work, but once you start traveling at a certain percentage of speed of light, it's completely wrong. If you didn't know about relativity and wanted to start considering, how light is bent around the sun, F equals ma would give you no insight whatsoever. So even there, it's very clear that theory has jurisdiction, limited jurisdiction. Relativity is wrong. I haven't got an example to tell you where. You just know it has to be. It's very comprehensive. It explains an awful lot, but it says nothing about the center of black holes. So it has limited jurisdiction. So even those very very central tenets of physics, we already know of cases where they don't apply. The constants of physics aren't constant. They're constant now. Or they look constant because they've seemed constant over millions of years. But there's evidence that they're changing. So in the hardest of sciences, we can see that the theories are limited. And if you try and apply F equals ma to interstellar travel, you're going to get the wrong answer. So even there, you have to have a very good understanding of how your assumptions behind that theory limit its applicability. Does that help at all?
Thank you.
Hi, Kurt.
Hiya.
My name is Mary. I'm taking an MSc, reading a question from the group. One thing that I actually really connected with is your advice to us, and that all perspectives, theories, frameworks should be regarded as limited, provisional, and subject to change. And that is really awesome, because I think a lot of that does need to change. And so it kind of brought me to a question, and it is based on the article that we read, The Hegemony of the Physical Sciences, and that you had mentioned that you wish to revisit the conclusions of another published journal because your point of view had changed slightly. And I'm wondering what you discovered in regards to your own systems thinking and how this will change your current or future research.
Well, in some respects, I see that paper. The purpose it served for me was as a kind of a ladder to climb to get to a point where I didn't believe in anything. It's kind of enabled me to get to a point where in the Buddhist sense, there's nothing but emptiness. So if you want to say something that's absolutely true, you can't say a thing. There's nothing that can be said that's so general and all prevailing. And then I kind of throw it away, and it becomes more of an outlook, a philosophical position by which I judge or I make assessments of new things that I'm exposed to, things that I read. And that was really valuable for me because, as I've kind of hinted at earlier, I mean, physicists tend to be taught in a way that, there's a right way of doing things and there's a right perspective. To get to the point of really deeply, fundamentally understanding and appreciating that all perspectives have merit. And now, of course, this is not saying that all perspectives have merit in every circumstance. This is saying a good default position to start at is just stay open-minded. Don't dismiss stuff because in certain areas it makes no sense whatsoever. In other areas, it may be useful. And for a lot of problems we look at, you can work through a critical thinking process, and you discard some of the more out there ideas fairly quickly. But they've got to be dismissed for a reason through assessment, rather than just like, oh, that's a load of rubbish, we're not going to consider that one. A lot of you kind of see that sometimes where you trying to compare kind of native theories about their ancestors and how they impact their lives, and it sounds very kind of out there and a bit spiritually wishy-washy, and it can easily be dismissed. But if you look deep into it, you find there's merit there, even if it's not absolutely true. And I think different explanations can be transferred. But as to my own research, I'm so hung up on the game of life that if I could retire tomorrow with $10 million, that money would all go into a massive computer where I would do what they do in a Hitchhiker's Guide, build the computer to model it all and see what it's all about. But probably going a bit far there. But I'm interested to see what more can be extracted from that model. I'm almost convinced that if it was big enough and the rules were right, that you would observe entities that were essentially sentient for all intents and purposes. And I think that'd be stunning to see that type of phenomena emerge from something so simple. If you look at neural networks today, it's kind of trying to hard code these things, program sentience. The idea that our abilities that we seem to have, that seems to set us aside from so many other species, is nothing more than an emergent phenomena that was inevitable once chemistry kicked off. I think is absolutely fascinating. So in some respects, the philosophy is done, and it's got to a point where, well, there is nothing. So now I've got to figure out how to work with that, continue to be useful, and pay the mortgage. And
Thank you very much.
Bit of a wandering answer, I'm afraid, but.
Team 2.
Hi, I'm Justin. I'm calling Marlo. Most of the people in this room work in ecological sciences and ecology management. It's a sector that tends to be very prescribed and regimented or regulated. You mentioned that you've done some management consulting, and I'm curious if you have or how you envision shifting that sector from the heavily linear, regulated thinking to the more complex or abstract thinking.
Well, I haven't myself in particular in that area, but what strikes me a lot, in government and policy making is how, as you say, how prescriptive the policies are, and how hard it is to change policies when they're clearly not working anymore. It's. I mean, I can't put words in their mouths. I don't speak to policymakers on a daily basis in that field. But just from the outside looking in, it all too often seems that to me that there seems to be a lack of recognition that policy changes the system you're trying to regulate, and so what you're trying to regulate won't be there necessarily in a decade's time, and policy needs to evolve. It really wound me up when I think John Kerry in one of the presidential elections got accused of being a flip-flopper, and he had no defense for it. I mean, he was being accused of being somebody that didn't stand fast on a particular idea and go through with it regardless of the consequences. I mean, that just seemed a very easy accusation to defend yourself against, and yet he couldn't somehow. So I think that's it's a bit like in project management. In project management now, they've actually, if you do the formal project management training, they have there's a module in there or an activity that's through which you're supposed to keep monitoring the project in kind of a detached way. Does it still apply? Are the assumptions we made at the beginning, are they still valid? Is our goal still the same as it was at the beginning? This kind of meta activity where we still plow ahead with the project and we still have a plan, we still have tasks, but at the same time, there's an ongoing review of whether any of that's relevant anymore, or does it have to be changed? And I think that kind of meta policy analysis, if you like, is somewhat missing. There seems to be a kind of commitment or escalation of commitment where we worked so hard to get this done. Let's just keep it because it's so hard to get there. Let's just stay with it. But then on the flip side, how frequently should you change and adjust? It's policy in an area where the objects of analysis really are very hard to pin down is very difficult. So you kind of have to stick with something to see whether it's worked. How long do you stick to it when you see it's not working? Do you kind of hope that it will work eventually, or do you change? And I think they're all very difficult questions to answer in a general sense, other than these are things to keep on the lookout for, to be actively monitoring the success of a policy, gathering evidence as to whether it's working or not, and to critically evaluate it at whatever frequency makes sense. So I think that's, and I'm sure, as I found with a lot of different fields, the best people are doing that already. It's just not as common as you would like it to be.
Yeah, not at the industry level.
Yeah.
Thank you.
Hi.
Hi.
So you explained there's a different perspective. There are different perspectives, and they're all real and not real at the same time. The distinction between what's real and what's substantially real is small. The subtleties are different, but the subtleties are different between capitalists, scientists, Marxists, religionists, as well as what makes each of us intellectually unique. How have you found is the best way to break down boundaries of different perspectives in your personal life? And are these techniques able to be used in different situations?
Well, I mean, it's not an area that I've developed many tools for and approaches for, especially. But I've been involved with some groups that look at decision-making tools that try and deal with some of these issues. And I don't know if this is a relevant example, but there's tools in causal mapping and I think it's called system dynamics, where a big part of the process is to try and uncover everybody's assumptions, rather than just let people make statements and stand by them. It's to try and understand where they're coming from, to have that kind of interactive conversation, to do some modeling, to perhaps show in a way that's convincing to some people that the assumptions they have just don't apply in this situation. But that doesn't happen by somebody just saying you're wrong. It happens by supporting critically, facilitating a kind of critical interactive process. And there are you just got to Google critical facilitation techniques, and you'll find lots of examples on that. But it's the idea that it's the engagement that's important to bring people around to not necessarily to the same answer, but to enable them to understand their perspective, the strengths and weaknesses of it, and then you can begin to explore, well, how can we kind of work towards some kind of agreement for this particular context. it's the kind of statement I make in the paper about everything being equal only really applies in the general sense, and it's really just a response to, at the general level of everything, there is nothing you can really say that is true all the time, which hopefully is fairly self-evident. But that's not true in a particular context. In a particular context, I think it's easy to acknowledge that there are some things or some views and opinions and approaches that aren't especially useful in certain contexts. We can start to whittle down the parts of our thinking that are useful in this area and the parts of our thinking that aren't especially useful in this area. But in some of the critical dialogue approaches, the key is to get buy-in. And the only way you get buy-in really is for people to, through this interaction, I don't want to get too fluffy with the process, but through this interaction, a perspective will emerge, and the people involved will appreciate where that's come from, why they got to that end point, even if it conflicts with some of their, deep central beliefs. Maybe they're more willing to suspend them for this particular problem that we're trying to solve. So I think exposing is the wrong word, but making trying to understand our own thinking at that deeper level and putting it out on the table, or getting it extracted and exposed to everybody as part of that process is really quite essential. Because it's not just saying you're wrong or I'm right. It's in this particular case where we're trying to solve this particular problem, there are ways to do things that might create some conflict within me, but I can understand where it's come from, and I'm willing to accept that and move in the same direction. So it's but I'm sure there are plenty of examples where people have tried to do that and it just ends up with a fight. So it's a very difficult area, and I think the area of facilitation of critical constructive meetings is a very, very difficult skill. And I think I read a paper once. It was compared to some area of nursing. I can't remember what it was. I think it's to do with what are the nurses that specialize in birth? I can't remember what it's called. But that it was, it's a very, you really got to be switched on and understand how people are thinking and how easily they can take offense and how they can be coaxed in a certain direction, and how managing that process is an incredibly skillful thing. I haven't got it. And we don't see enough of those. I don't see enough corporations, for example, governments trying to bring in people to help those processes, to support critical group facilitation approaches. Surprisingly, the army are very good at it. Sometimes we think the army are just like, hey, go drop bombs. This is great fun. We'll just go in and there's a problem. Let's just shoot them down. But of course, they're not that keen on losing people either. And some of the decision-making processes, some of the Navy and Army have are very, very sophisticated, and it's not too apparent to the outsiders looking in of how sophisticated some of their thinking is. And I think there's a lot of industries that could learn an awful lot of how they plan. I mean, again, when it's presented by, in some ways, it just seems like a hammer running around looking for a nail to hit, but I think it's rather more sophisticated than that. So I hope that helps. I didn't really talk about group facilitation at all, but I think that's an area that kind of makes similar assumptions about the nature of our thinking, the relationship between us and the problems and contexts we're trying to engage with. And it tries to provide a framework to enable that to happen, and at the same time acknowledging the framework itself is limited.
Okay. Thank you.
So, hi, Kurt. Thank you.
Oh, very welcome, Alice.
To almost see you. That was very interesting. As I think you know, you've been the third and final systems guest we've had, and the language used, as you can imagine, and the examples used have been really different in each one. So I'm hoping people are making some good generalized connections across these different. And personally, I wanted to thank you for one of your answers where the team asked you about, you know, why that paper. That wasn't their wording, but several people said to me, that's an older paper. Why did he choose that? And I'd never heard you talk about, you know, getting to the point of that, you know, Buddhist emptiness and sort of setting aside those tensions and then moving on to be, you know, functional in the world. I find that really, really interesting. So thanks for that. Yeah, we'll do a little bit of debriefing and you'll get some sort of a thank you in the mail. Do you have any final comments before we? Yeah, by the way, before you answer that question, Lois, the last speaker, I don't think you heard her when she was asking about examples from your personal life. So the conclusion I've come to is you really don't have a personal life these days. I know that's not quite true. Yeah, so any final thoughts for us?
Well, I say, but it's in some respects, my personal life is just wanting to try and understand things a bit better. That's all there is to it. You know, it's I'm reading a lot of medical books at the moment to talk about aging and how we're very close to being able to extend it arbitrarily. So I'm trying to plan out the next 1,000 years research program to keep me busy. But you know, I've appreciated the chance to talk to you guys. It's you know, some of the research I've done, I've not had a chance to look at now for a few years because I'm caught up with corporate stuff. And every time I get kind of invited to think about it again and explore it, I just wish that I could just retire tomorrow and do this and look at this full time, because it's so much fun. And in some ways, it's so rewarding because in the sense that, you know, I'm a bit more chilled out than I was 20 years ago. And some of that's, you know, I'm just getting older. But a big part of that was just coming to the conclusion that the things I thought I knew weren't necessarily wrong, but not to get too hung up on them. And, you know, shit happens and you deal with it. And it's going to continue to happen. And that's life. And enjoy the ride. And that's about it. I think thanks for your time.
Well, thank you very much. Thanks to Charles for introducing you and to everyone for their questions. And we actually have a recording of this now. So
oh no. remember I said that, you know, knowledge and thoughts and understanding, you know, change over time. So I could completely disavow any of this, you know, a few short weeks from now.
Thank you.
Thanks, everyone.